Okay, so far we have this idea of exponential growth going on. I've just written down a few examples of what we've looked at. So we start off with y equals 2 to the power of x, which literally says that 2, this base down here, tells you what you should multiply by every single time period. Then you had y equals 3 to the power of x, and the 3 tells you what you should multiply by every single time period, and the same with e. And actually we looked at e in the last example, okay, and we literally said that if you have a situation that models continuous growth, the chances are it's going to follow this number down here, where e is like 2.718, etc, etc, etc. Okay, so if you have a situation in nature that is growing exponentially, it's usually going to be described by this equation here. Okay, now just for the sake of argument, I'm just going to go back to y equals 2 to the power of x, because it's slightly easier to think about. This table here we've already come up with. So remember, I said that x could be, for example, time, and y could be the amount of money you have in your bank account, or it could be describing population, or it could be describing radioactivity, or it could be describing computing power. I don't mind, okay? It could just be over here. So let's say that y represents population and x represents time, okay? So for every single time period, if it's being described by the equation y equals 2 to the power of x, okay, at the start I should have 1. I should have one thing in my population. Then maybe one time period later, I should have 2 things, and then another time period later, I should have 4 things, then another time period later, I should have 8, another time period later, I should have 16. So what this equation literally tells me at the moment, so y equals 2 to the power of x, what this equation literally tells me is it says, right, you give me time. Okay, you give me time. So in other words, you tell me how long your population has been growing for. Okay, and I will tell you how big the population is. So in other words, I will tell you how big the population is. I will tell you size. Okay. Now, wouldn't it be nice if I could ask the reverse question? In other words, what if I knew that y was equal to 256? So I knew that there were 256 things in my population, but I wanted to work out how long my population had been growing for. Is there a way of doing that? So in other words, I want to not just give you time, I want to now give you size. I want to give you how big my population is, and I want you to tell me how long I've been growing for. Okay, so I want to ask the reverse question now. Is there a way of doing it? So y equals 2 to the power of x says, you give me time and I will tell you how big it is. Now I want to come up with a way that says, I want to give you size. I want to tell you how big it is, and then you tell me how long it's been growing for. Fortunately, there's a really lovely way of doing this, and it's something called a logarithm. Okay, so a logarithm is just simply a way of reworking this such that now it can give you x. So you give me the population and I will give you x. Okay, I'll give you how big it is and you give me x, you give me time. Okay, and you just simply rewrite it like this. So x, the thing which I'm after time, okay? The way which I get it is by finding a logarithm. So I just abbreviate that to log for logarithm, okay? Well, I need to tell you what's happening for every single time period. So remember, from here to here, I'm just simply multiplying by 2. Okay, so my growth factor is 2 for y equals 2 to the power of x. So you need to tell me what's happening for every single time. So we put that down here. Okay, so log and then a little 2 down here, just to say every single time period you're doubling. Okay, and then you need to tell me your population. So you need to give me y. Okay, so this idea here, x equals log to the base 2 of y. Okay, this simply says you tell me how big your population is, and I will tell you how long it's been growing for. Okay. Now, if I give you y equals e to the power of x, for example, y equals e to the power of x, right? If I wanted to rewrite this, okay, simple way of doing it would just be write x equals log. I need to tell you what the growth factor is each time, which in this case is e, okay? And I also need to give you the size of the population, so I need to give you y, okay? Now, remember that we said that y equals e to the power of x represented natural growth, okay? So growth in nature typically follows this because it happens continuously without stopping. Okay, so because this is a natural growth function, then surely this should be the natural logarithm function. In other words, it gives you the time if you tell it the size. Okay, so we just simply rewrite it. Instead of writing log to the base e, we write it as the natural logarithm. So we say ln for log naturel, it comes from French, okay, or natural log of y. Okay, so if you see these two things, if you see ln of y, it just simply means log to the base e of y. Okay, so in general, a logarithm is just a way of reworking this equation such that instead of giving time, it gives you size and it tells you the relevant time. Okay, and if you see this, it's just a natural logarithm. Okay, now, if you remember right back to the very start when we first started looking at logarithms, we came up with this fundamental situation. So if we had y equals some base, let's say 2 to the power of x, okay? We said that the definition of the logarithm, one of the definitions of a logarithm, is that the rate of change should be proportional to its size. Okay, so if this is your size, okay, the rate of change is proportional to its size. So in other words, the bigger it is, the faster it can grow. Okay, the bigger it is, the faster it can grow. Or if you wanted to rework that, you could write it as an equation by saying it's just some multiple of your size. Now we said that if you have this special base, this e to the power of x, and we've looked at that now, if you have e to the power of x, then you're basically saying that the rate of change is no longer just proportional, it's actually equal to its size. Okay, so in general, proportional means that the bigger something gets, the faster it can grow by. In this case, so the bigger the size gets, the faster it can grow by. Okay, and it's always going to be off by some constant. So it could be 3, it could be 4, it could be some decimal. Okay, so proportional in general means it's always going to be some multiple of whatever its size is. But actually, with e to the power of x, another interesting thing about e to the power of x is that the rate of change is not just proportional to, it's actually equal to. So in other words, if I try and differentiate e to the power of x, that is actually the same as whatever my population is. So in other words, whatever e to the power of x is. Okay. Now, I can use this to try and work out what the natural logarithm differentiated will be. Okay, so if I try and differentiate the natural log, by the way, this symbol here, this d by dx, simply just means differentiation. Okay, differentiate this, it's an operator. Okay, differentiate this thing in here. Okay, I can use this idea which I looked at up here to find out what the derivative of the natural log is. Okay, so let's look at this. Okay, let's look at this. What I'm first of all going to do is rewrite y equals log to the log of x, okay, natural log of x, as a power, okay, so in exponential format, okay. Let's have a look at this. I have y equals log of x, okay. If I was going to rewrite this, it would be x equals e to the power of y. Because remember, x represents, in this case, your population, and y represents your time. So if I wanted to rewrite this, it would be written as this, okay. If I wanted to rewrite it, it would be written as this. So if I differentiate this, okay, I know what this thing differentiated is going to be. So in other words, because I have x as my function and it's in terms of y, it means that when I differentiate it, I'm going to differentiate x with respect to my function of y. So I'm going to find dx by dy, okay? So I can find dx by dy quite simply by knowing that the rate of change of this thing should be exactly equal to its size. Okay, because that's literally exactly the same idea as I had up here. So in other words, if I differentiate e to the power of something, that should be exactly the same as e to the power of something. That comes from our definition of exponentials. Okay. Now, if I think about this, okay, I don't want to differentiate e to the power of y. I want to differentiate this thing. I want to differentiate log of x. Okay, so I want to find dy by dx. That's what I'm after. So in other words, I don't want dx by dy. I want dy by dx. Well, I can really simply do that by noticing that e to the power of y is given by x. Do you see that? E to the power of y is just x. So in other words, I could say that dx by dy is simply just x. Which means that if I want dy by dx, that's just the reciprocal of that. In other words, just being flipped upside down. Okay? So in other words, dy by dx should just be the reciprocal of x, which of course is just 1 over x. So in other words, if I have y equals natural log of x, the derivative of that, dy by dx, is just 1 over x. Okay, so y equals log of x, natural log of x. That means the derivative of it, dy by dx, should just be equal to 1 over x. So that's a fundamental idea just there.